Today's learning goal is to explain Kepler's three laws of planetary motion. Explain Kepler's three laws of planetary motion. We're talking about the birth of modern astronomy. We're going to begin our discussion with this guy named Nicholas Copernicus. He was a Polish mathematician, astronomer, economist, physician, governor, translator, diplomat. These guys, they got into a lot of different fields and they were super, super smart. And Copernicus was interested in improving Ptolemy's model of the solar system. So Ptolemy's model was getting kind of old at this point. It wasn't doing a good job of predicting the position of the planets. It had to be constantly revised. More epicycles needed to be added. It wasn't doing a good job. So he wrote this book on the revolutions of celestial spheres, where he presents his heliocentric model of the solar system. So he puts the sun at the center of the model, and he says, look, we can describe the solar system this way. It makes the geometry much, much simpler. Take a look. This is actually the picture that he publishes inside of the book. This is the diagram. He puts the sun at the center, and then take a look at the order of the planets. Mercury, Venus, the Earth with the moon revolving around the Earth, Mars, Jupiter, and Saturn. Incredible. So he gets the order of the planets correct. He puts the sun at the center, and now you have this series of concentric circular orbits. Beautiful, easy to describe, much less complicated than all those loops. And then he dies, and he just kind of leaves it to the world to deal now with this chaos that's gonna follow. And one of the people that received the consequences of that sort of intellectual chaos was this man Galileo Galilei. Let's watch a video about him.
It's 5 p.m. on Thursday, the 7th of January, 1610. Galileo Galilei is in his garden in Padua, northern Italy, where he is just about to make a revolutionary decision: to point his newly constructed telescope for the first time in humanity's history towards Jupiter. Little does he realize that this simple action will utterly change the world forever. With a simple turn and point, the final chapter in a long and bitter debate about our place in the universe will begin. But how did Galileo get to this point? How did he get to this moment, alone, under these darkened skies, diligent and determined? Welcome to Savantium. Part of the answer lies 2 years earlier. It's the 17th century. The fifth Mughal emperor, Shah Jahan, has just commissioned the construction of the Taj Mahal in Agra, India. The Romanovs have just gained control of Russia, a dynasty which would reign for over 300 years until its definitive end in 1917. Meanwhile, in Europe, the first cracks of the Spanish Empire's Siglo de Oro are beginning to emerge. And this is where the seeds of our answers lie, where a new nation has just gained its freedom and is fast gaining momentum and influence. It's late 1608, and this new nation, the Dutch Republic, is on the up. Capitalism and innovation are rife. The Dutch own world trade and will soon reign supreme over the seas, with a competitive edge on innovation and science. Optimism, openness, experimentation, and daring are the currency of the day. And beginning in the 1590s, glassmaking and lens grinding techniques have also been vastly improving. It's only a matter of time until someone holds two lenses together and discovers just exactly what they can do. And it is one such man from the coastal town of Middelburg, a lens grinder and spectacle maker named Hans Lippershey, who is the first to act. And on the 2nd of October, 1608, he lodges a patent to the state in The Hague, noting a Dutch perspective glass which serves to see things far away as if they were nearby. An extended eyeglass, in other words, which is soon to be known as the telescope. The first stages of the scientific revolution have begun. And in only a matter of months, word of this revolutionary device would spread far and wide throughout the kingdoms of Europe. eventually falling into the hands of some of the greatest minds of the age. Court mathematicians, professors, and astronomers like Simon Marius, Thomas Harriot, Johannes Kepler, and of course, a 45-year-old Italian polymath named Galileo Galilei. It's June 1609. Galileo is in Venice when he first learns of this Dutch perspective glass, which increases human vision by a factor of 3, as news of Lippershey's invention continues to quickly spread. Galileo has no time to waste, and on that very night, on his return from Venice to Padua, he gets straight to work and commits to building his very own version. Within days, he's designed one. And in less than 2 months, on the 25th of August 1609, he demonstrates his telescope to the Venetian lawmakers and offers it as a gift to the Senate. With 8 times magnification, the Senate quickly sees its military potential. After winning the favor of the Venetians with his gift, Galileo decides to turn his telescope towards the skies, to more peaceful and infinitely more curious endeavors, our universe. A device for war and devastation is now destined for exploration. Galileo's final telescope is exceptional for the day, ranging 20 meters in length, 37 millimeters in diameter, with the ability to see 20 times more than the human eye. It is formidable. This simple idea to improve a nascent technology is the very first steps to the heavens, and together with his mathematical abilities of recording, precision, and rigor, it's a recipe for scientific revolution. He first points it towards the moon, where he observes craters, grooves, and mountains in what was always presumed to be a smooth surface moon. He next observes ribbons of diffused light that arc over the sky, our Milky Way galaxy, which he now realizes is composed of many stars. And then, a little over 3 months later, Galileo's investigations take a dramatic turn. Under the clear night skies of Padua, he points his telescope for the very first time towards the gas giant Jupiter. This simple decision changes everything. And so, on this unassuming Thursday evening on the 7th of January at approximately 5 p.m., armed with only his notebook and his telescope, Galileo observes 3 fixed stars, which he scribbles are extremely close to Jupiter, 2 on the east and 1 to the west. He continues to observe these objects on subsequent nights and realizes that these 3 stars are in fact wandering like satellites around Jupiter. And these objects often obscure one another, falling in and out of range, so much so that Galileo misses the full amount of objects in Jupiter's orbit. And by January 13th, and much to his own confusion, he now glimpses 4 objects moving about Jupiter. By January 15th, he fully confirms that a 4th satellite is in existence. The moons of Jupiter are finally unveiled: Io, Europa, Ganymede, and Callisto. The realization is now clear. Jupiter, too, like Earth, has moons. And these moons, too, rotate around Jupiter just as our moon orbits the Earth. The ramifications of this moment are immense, because now he realizes with irrefutable proof that the Earth is not at the center of our universe. And so Galileo hurries to make his discoveries known, and in a little over 2 months of pointing his telescope towards mighty Jupiter, Galileo publishes 500 copies of his findings in a 24-page pamphlet called Sidereus Nuncius, better known as the Starry Messenger, in March of 1610. The book sells out almost immediately, creating a veritable sensation across Europe. At long last, heliocentrism is here, a view that since Aristarchus was silenced by fear. As for Galileo, the battle has just begun. He will spend the rest of his days observing the skies and battling the church with irrefutable proof that we too orbit the sun. Never has such a simple gesture as pointing a stick to the sky, as Galileo did with temerity and curiosity in 1610, had such immense ramifications for the future of humanity. A scientific revolution held together in 20 meters of wood and glass is unleashed on the world, and the floodgates of scientific learning now pour open.
Okay. So, quick summary. Galileo uses his telescope to confirm the heliocentric model of the solar system. He uses 2 key pieces of evidence. One is finding that Jupiter has moons. Take a look, these are his drawings from his notebook. So here's Jupiter, represented as a large circle. And then these little stars, these are the 4 giant moons of Jupiter. So this gives some evidence that the Earth isn't the only planet that's at the center of other objects. There are objects that orbit Jupiter, for example. He also looks at the phases of Venus. So sometimes when you look at Venus through a telescope, it looks like a little tiny crescent moon. It's not the moon, obviously, but it looks similar to what we see when we look at the moon and it's in its crescent phase. Sometimes it's completely illuminated, like a little disk. And this gives evidence, right, that Venus is actually going around the sun, and he's able to show this. So he starts lecturing about it. He writes books. He writes books and lectures in Italian rather than Latin. So like common people are able to hear about these ideas, and this makes the church very nervous. They like to be the ones that are controlling the information. The Catholic Church gets angry with him, puts him under house arrest. He actually ends up dying while he's arrested at his house. They ban his books for 200 years. They bury him outside of the church, just as like a final sign of disrespect. And yeah, but this has like an important. It's very important for the future of science. Okay, so let's move on now to Tycho Brahe and Johannes Kepler. So now we know that the sun is at the center of the solar system. Tycho Brahe, he's a Danish astronomer. He has 20 years of continuous data on the position of the sun, the moon, and the planets. This is very critical. All this data can be analyzed and used to come up with some models about the behavior of the planets. He's not smart enough, or maybe he's too distracted to be able to do this analysis. He's kind of a party animal. Look at his nose. Do you guys see that something is kind of strange about his nose? He actually got in a fight with someone at a wedding. He challenged them to a duel, got his nose cut clean off of his face. He had to wear a prosthetic nose made out of metal. He also has lots of crazy, there's like lots of crazy anecdotes about his life. He had a pet reindeer. He would give the reindeer beer. One time the reindeer had too much beer and he fell down the stairs and died. He was once at a party and had to get up to go to the bathroom, but he thought that it would be rude to do that and he didn't do it. He just like stayed in the party. Later after the party, he realized that he couldn't go to the bathroom. 11 days later, his bladder exploded and he died. Very bizarre. But while he was alive, he started working with a young mathematician by the name of Johannes Kepler. Kepler was incredibly smart. He could analyze Tycho Brahe's data, but Brahe had very tight control over that data. Didn't want Kepler to get a hold of it. He thought Kepler would be able to analyze it and figure out the secrets to the solar system, and then Kepler would get all the credit and Brahe would get none of the credit. Some people actually think that maybe Brahe was murdered by Kepler. Analysis of Brahe's bones showed that he had a high concentration of mercury in his body. So it's possible that Kepler killed him. He had motive to obtain the data, because once Brahe died, Kepler inherited the data, and he basically was able to figure out how the planets moved around the solar system. So Brahe dies, Kepler inherits the data, publishes 3 laws. Let's take a look at these laws. So they're called the laws of planetary motion. Kepler's first law of planetary motion says that the orbits of planets are elliptical. So ellipses are like flattened circles. And they have two foci. They have a focus here and a focus here. Plural of focus is foci. Two foci. The long axis of the ellipse is called the major axis. The short axis of the ellipse is called the minor axis. Half of the major axis is called the semi-major axis. Okay. So he says the orbits of the planets are ellipses, and the sun is at one of the foci. So the sun is at the focus. The other focus is empty. This is Kepler's first law of planetary motion. Kepler's second law of planetary motion. This one's a little tricky. I think this is the hardest one to understand. But let's try to think about it. So imagine if you drew an imaginary line between the sun and the planet. As the planet went around the sun, imagine 1 day in the orbit of this planet. That imaginary line would sweep out an area that looks like this. So if that takes 1 day to sweep out that area, when the planet is over here and it moves for 1 day, it'll sweep out an area like this. So a little bit of a fatter triangle over here, narrower triangle over here in the same amount of time, but both areas will be equal to each other. So this is the windshield wiper law, or it's also called the equal areas in equal time. But the implication is that the planet moves real slow as it's really far away from the sun, and then when it's coming close to the sun, it speeds up, and then right here, it's moving the fastest. So slow when it's far away. You can think about it, it's like falling towards the sun, speeds up, and then as it's moving away from the sun, it's slowing down, and then speeding back up as it comes back around. Here's an animation, you can take a look. So the idea is the area of this wedge is always the same as we're seeing it go around. So the wedge is going to get fatter when the planet is close to the sun, and it gets like skinny but long when it's far away from the sun. So planet moves slow when it's close to the sun, planet moves fast when it's planet moves slow when it's far from the sun, planet moves fast when it's close to the sun. Okay, Kepler's third law. This one is the mathy law. Okay, we have to think about math a little bit in this one. So Kepler's third law of planetary motion says that the square of the orbital period is equal to the cube of the semi-major axis of the elliptical orbit. Okay, let's think about it one more time. So the square of the period squared, is equal to the semi-major axis cubed. Okay, this is a little bit intense. Let's make it easy. Orbital period is the time that it takes for one complete orbit. So for the Earth, that would be 1 year. The semi-major axis is simply the average distance between the planet and the sun. Easy. So A is average distance, P is orbital period. And in order for this equation to work, because actually these two things are proportional to each other, so they're only equal if we use very specific units. So those specific units are Earth years for the period, and astronomical units, or AU, for the distance. Now, what is an astronomical unit? An astronomical unit is the average distance between the Earth and the sun. So how far away is the Earth from the sun? 1 astronomical unit. Okay, let's take a look at a couple problems. Kepler's third law, example number 1. We're going to confirm Kepler's third law for the Earth. Confirm Kepler's third law for the Earth. Very easy. First thing, we'll write down Kepler's third law. P squared equals a cubed. So the orbital period for the Earth is 1 year. It takes 1 year for the Earth to go all the way around the Sun. The average distance between the Earth and the Sun is 1 astronomical unit. So now let's plug these two things into this equation. Stop the video now. Okay, hopefully you plugged in both of those numbers. Let's take a look at what we get. So 1 squared is 1, 1 cubed is also 1 equals 1. Therefore, Kepler's law works for the Earth. And you can try this for all the planets. You can look up what's the distance from the Sun, how long does it take for it to go around, and you'll get approximately the same two numbers when you square one, cube the other one. Let's take a look at this one. So this one's a little bit trickier. It says, it takes Jupiter 11.86 years to complete one orbit around the Sun. How far is Jupiter from the Sun on average? Okay, so first thing, write down Kepler's third law. P squared equals a cubed. So let's take a look. It told us that it takes 11.86 years to complete one orbit around the Sun. That sounds like orbital period. So we're going to put that in for P. So P is 11.86. And then we have to square it and set it equal to a cubed. So the average distance cubed. Let's plug this into the calculator and find out what this is. 11.86 squared. So if you multiply 11.86 times 11.86, you're going to see that it's 140.66, and we're just going to leave the other side of the equation alone. So now we know what the average distance cubed is, but that's not what we're trying to find out. We're trying to find out what is the average distance just by itself. So how do we undo the cube? We should use the cube root. So we're going to cube root both sides of the equation. Cube root of a cubed, cube root of 148.66, and the cube root will cancel the cube, which gives us just a as the average distance. And on the other side of the equation, we should plug this into the calculator. Cube root of 140.66. We get 5.2 astronomical units. Okay, now you try this one. We'll go over it together in a little bit, so pause the video. Okay, let's take a look at how you did. So the semi-major axis of Mars' orbit is 1.52 astronomical units. How long is a Martian year? So we're interested in finding out what is the orbital period of Mars. So we've got Kepler's third law, P squared equals a cubed. We're being given the semi-major axis of Mars' orbit. That's a, the average distance between Mars and the Sun. 1.52 astronomical units. So we're going to substitute that in for a in our equation. So we have p squared equals 1.52 cubed. So we should plug this into the calculator, multiply 1.52 times 1.52 times 1.52. And that comes out to 3.51. So p squared is 3.51. Now, we want to know orbital period, not orbital period squared, so we have to undo this square. How do we undo the square? Square root. So we're going to take the square root of both sides of this equation. Take the square root of p squared, that's going to give us p. Square root of 3.51 gives us 1.87, and our answer has a unit of Earth years. So Mars takes 1.87 Earth years to complete one orbit. And that's the end of our lesson. Great job, you guys.